So here we have part 2 of the physics test 3. I looked at this problem and I saw that it was a flux problem with a graph, so I decided to make an expression for our changing flux because I figured that would be useful later. So we have our expression for our derivative of our flux is the same as our derivative of b times a, but in this problem b is a constant 15, so that gives us b times the derivative of a. So here's our little expression that we'll use later, 15 times dA dt. And obviously here's our graph of dA dt, and we'll use that later. So first for part A, we know that the induced EMF equals a negative d phi dt. And so our d phi dt up here, we pull that down, equals negative 15 times dA dt at t equals 1, which, as we can see from the graph, there's no change. So if the area isn't changing, the magnetic field isn't changing, the flux isn't changing, there will be no induced EMF. So we get 0. And that brings us to part B, where we do have a change in area. So there is a change in flux and there is an induced EMF. So we have the same expression, negative 15 times dA dt at t equals 4. Now we go up to the graph and we can see that here our derivative is constant, and you can just calculate from the rise and the run, negative 4, positive 3. So our derivative through this area is a constant negative 4/3. So we just plug that in down here. Negative 15 times negative 4/3 gives us 20 volts. And in terms of a direction for that EMF, or for the induced current, because the loop is getting smaller and the flux is decreasing, there will be a magnetic field induced in the same direction. So that would be pointing out, and then from our right-hand rules, we can see it would be curling counterclockwise.